And so let me start off by saying welcome to the first in a series of PyHEP working groups, module of the month, where each month, the first Wednesday of every month, we will be talking about some Python module that we think is very helpful for data analysis. This month, I'll be talking about Numba, the just-in-time compiler, and I'll have plenty of introduction for that. So as you can see, we have already planned for next month, we'll be talking about JAX. And the month after that will be PyHEP. And we are continuing to fill up the calendar with interesting things to talk about. So first I'll talk a little bit about the technology so that get you all started on this. Our Indico page doesn't have very much on it, just a link to Zoom, which I don't have to tell you about because you're all here. You're the people who found it. And a link to the notebook on GitHub, where all the rest of the information is. These talks will all go onto a YouTube channel. That's what we're recording right now. And there isn't anything there yet, so it's just got this blank video page because this is the first one. This is the GitHub repo. And I'm going to ask for you guys to follow along in Binder because I'll be asking questions as we go, and I'd want you to experiment. When you click on that button, it will launch a Jupyter notebook in your browser that's the same as my Jupyter notebook, except I think the version is different, so it looks a little bit different. When you are running this on Binder, you can evaluate the cells and you can explore, just like I can here. But if you let it sit for a long time, it'll lose the connection and then you have to reload your page. So I'm just saying that if you click that now and you get started with the Jupyter notebook now, by the time we actually get to it, you might need to reload the page. Next thing is that I'll be taking questions on Slido. That's this thing here. And I'm going to ask everybody who's already here to either point a phone at that QR code or go to slido.com and enter in the number 70783 and test it out by asking test questions like, just say hi, just say whatever. I should point out that I'm also monitoring chat. So I see that Abraham has just said, copy the notebook to Swan area. Maybe others will find that useful. That could be good, it's true. If you're comfortable with copying it to Swan and doing it in Swan, you can do that. But also note that Binder works. You just click on it and you can just get started. So that's the least effort way of doing things. So I'm also looking at the participants list, so I will see if you raise your hand. So if you want to raise a hand and ask a verbal question, we can definitely do that. But this, I think, is going to disrupt the flow less because you can type this while I'm still talking and you're not, interrupting. Oh, that's nice. And after I ask a question or I ask how does people think we can do this, you can, like you've just done, just type stuff in. You can upvote each other's things, so try that. Upvote, random questions and drive one to the top. We should be seeing here, there we go. Meaning of life is just shooting up to the top. Everybody likes the meaning of life. Okay, so so this is a way that even if you're shy, you can get this. Like notice that nobody's changed their name yet from anonymous. You can set your name whatever. All right, and then after I've said something, or we've gone into something and I'm moving on, I am going to periodically flush that so that the stuff here pertains to what I've recently been talking about. And with that, I will get into the subject matter. So the slides and the notebook are both on the both on the GitHub page right here, just as a reminder. There's the slides. Okay, so Numba. Actually, this tutorial is more getting Numba to do what you want, because I am acknowledging that it's not always the easiest thing to do. So let me start with the big picture. To optimize or not to optimize. So scientific computing is of two minds about accelerating code. Sometimes, when we don't have a specific problem in front of us, we often say things like, oh, tweaking performance should take a backseat to the science. The science is much more important than trying to get things just a little bit faster. But then sometimes, when we have a real problem, we often are saying, well, if it doesn't run within the time and memory constraints, we can't do this measurement. So it absolutely does matter. And so there's this kind of tension whenever we're talking about scientific computing. Now, of course, both of these are true, obviously. The science is more important, but if you can't do the science, that's a problem. So the objective metric that we usually talk about is time to insight, which kind of balances both. That it needs to run fast enough, but also you shouldn't need to, if you're going too far out of your way for a tiny computing gain, then you're not getting a human gain. So, so I'll be talking about compilation, and compilation is a great technique for making code run faster. Roughly speaking, you compile it and it runs faster. More precisely, it removes hurdles that take the slowness out of code. That's how I'd rather say it, rather than making it go fast. Because a particular, for a given hardware, a particular problem kind of has a natural fastest speed. It's just all of our usual tools for making programming easy, which is important, get in the way of that ultimate speed. So like, if you're using interpreted code, there's can often be like dynamic type checking, following too many pointers, non-sequential memory access, translating virtual machine instructions into real machine instructions, garbage collectors. All of these things make programming easier, but they also make it slower. They get in the way of the particular process's ultimate speed. Also, compilation is not a monolithic thing. So if you're used to doing a lot C++, usually think of compilation as a single step in the process. You edit some code, you call C++ my source code -o, and that executable is fast. But it's not necessarily the case. Compilation can be piecemeal and applied at any time. It can be applied while your code is running. There's this famous paper, How to Make Lisp Faster Than C. And Lisp is one of these interpreted, dynamically typed languages, like Python, but older. And so much work has gone into Lisp over the decades. It's like 70 years old now. Maybe 60, I'm counting wrong. That so much work has gone into Lisp that there are things that you can do that effectively compile it in little bits and pieces. And the little bits and pieces that this paper talks about is all of these things, just one by one, fixing all of those things in Lisp. And then it runs faster than C. Compilers are everywhere. So even Python is compiled in some sense. The source code that you write gets turned into numeric byte codes. That's what goes into those .pyc files you might have seen. Those numeric byte codes run in a virtual machine. So it's not removing a lot of the hurdles, but it's removing at least one. It's not scanning the source code over and over. Re.compile, regular expressions are turned into a finite state machine. Even if you don't say the explicit re.compile, it does turn it into a finite state machine to actually run the regular expression. Struct.struct, maybe you're less familiar with, but it parses bytes. It's all over the uproot code. NumExpert.evaluate, this is a good one to be aware of. NumExpert is a virtual machine that evaluates math formulas, and it is faster than NumPy, even though it's a virtual machine. And that's because it's not allocating arrays all the time. Roots, ginterpreter.declare, that's how you do it in PyRoot. Inside the quotation marks, you can put C++ strings, and roots cling will compile those strings of C++ code into native machine bytecode, and that's as fast as it can go. Roots rdata frame also uses cling, so if you define things in RDF. Numba and PyPy, which is getting closer to what I'll be talking about here, they compile Python, not C++, but they compile a Python language to machine native bytecode instructions. And then Julia is a language designed around this. So Python isn't a great language for compiling. Julia, they're trying to strike a balance with all these things. And the key thing here is this just-in-time compilation. The two main just-in-time compilers for Python, Numba and PyPy, they take very different philosophies, and so it makes sense that there are two of them. Numba runs within normal CPython. So, the Python you get by typing Python in the terminal, that can run all of the normal Python libraries. You can run Numba just right along with them. Whereas PyPy replaces the CPython process. Some versions of Python and some libraries work within it because people have gone through a great deal of effort to make that so. But in general, it's not the same environment. Numba only speeds up functions labeled with the numba.jit decorator, but PyPy speeds up the whole program. It's not an opt-in thing. It speeds up everything without any modifications. In Numba, only a subset of Python features and functions can be JIT compiled, but in PyPy, the whole language, everything's JIT compiled. And in Numba, the gains are typically factors of 100, hundreds, I should say. Sometimes you can get a gain of 1,000. Whereas in PyPy, the gains are often factors of several. Because it's using the standard Python language, there are some hurdles it cannot remove. And that's actually why I'll be talking about Numba today instead of PyPy. It's because when we really want it, we want big factors on very specific things. And so Numba's philosophy fits in well. But then there's this problem here that only a subset of Python features can be JIT compiled. And so you try to JIT compile something and it doesn't work, and it's frustrating. And that's what this tutorial will be about how to make it work. So what kinds of code can Numba accelerate? The types have to be fully known before the code runs so they can actually remove that hurdle. Objects must be replaceable with memory contiguous values. So that means Numba has to recognize the objects. The functions must have or be built from low-level equivalents. So again, Numba has to recognize the functions. So therefore, only Python libraries that have been specifically prepared for Numba work in Numba. Numba optimizes NumPy out of the box, so it's really targeted for optimizing NumPy. But awkward array has been extended as well. And at the very end of this tutorial, I have some awkward array examples, although most of it is really about Numba. We're also working on other scikit-HEP libraries like vector and hist, so you can fill histograms within the compiled loop and such. I work with Lorentz vectors. And so this kind of fits into Python's optimization mindset. Most scientific Python libraries in Python split into a fast math part and a slow bookkeeping part. The optimization is focused. We don't try to optimize everything. We only try to optimize the thing that matters. And so we have to define what matters. Yes, optimizing is, Numba isn't about accelerating everything, it's about accelerating the part has to run fast. Numba errors can be hard to understand and resolve. So that's what this tutorial is about, making Numba happy. Okay. If there are any questions on that, go ahead and put them in Slido. And otherwise, I'm moving on to the notebook. If you have opened, if you've not opened, if you've not launched Binder yet, do that because I want you to be running this along with me. And if you have launched Binder, you might want to test it to see if it's still live, like try to import NumPy. And if it's not live, then it gives you some error or something, reload the page. Okay, so looks like there's no questions on the presentation. Let's get into the examples. I'll use this to scroll around. Unfortunately, you don't have one of these table of contents. I hope that that migrates to Binder soon. So I'll be starting with some simple stuff. And then as a reminder, if there's anything, when we're running low on time, I'll probably have to jump to what people are most interested in. And then I will, I'll take votes on, what do people want to hear about. But for now, I'll start at the beginning. Does Numba work with PyRoot? Since you can load PyRoot and Numba in the same Python, you can use them together in that sense. They don't have explicit connections. Our data frame is separate from Numba. Numba is compiling Python, and our data frame, the strings that you give to our data frame are C++ strings. So and they're compiled with Cling. So they're just two separate things. Although our data frame, they've been looking into using Numba to accelerate Python functions as well as C++. Numba does not yet leverage Python's type annotations, and I will talk about that. They predated Python's type annotations by a lot, and are so Numba has its own type system, which they are translating now. But that's not. But yeah, you got to use Numba types if you're going to be explicitly giving types. On the other hand, usually you don't have to explicitly give types, and so we'll see some examples of that. Okay, so let me start with some simple stuff because some of you might have used Numba before and others not. Does Numba overcome CPython GIL? Yes, it does if you say no GIL equals true. So that's the thing to look up. No GIL equals true. Okay. And after I answer things, I will refresh them. Okay. So if you've, so let's assume that you've not used Numba before, and let's start with the basics. So Numba accelerates Python code by replacing, sorry, so the very basics, NumPy. NumPy accelerates Python code by replacing loops in Python's virtual machine with precompiled loops that transform data arrays into arrays. So let's say that you start with an array like that, data. It's just counting numbers. If you were to do the Python equivalent of this by creating an output array, walking over the input data and squaring every value, putting them in the output, that would be the pure Python way of doing this. It's slower than the NumPy way of doing this, which is to do this array at a time calculation. You take the whole data array and you say square it instead of writing an explicit loop. So by removing that explicit loop, we get something that's in microseconds instead of milliseconds. So this here is a factor of 300, eyeballing it. Now, if you have to compute a complex formula, NumPy would have to make an array for each intermediate steps. And there are tricks around that, but yeah, we're not getting into that. So let's say that you have energy, px, py, and pz, and you want to, calculate mass, e squared minus p squared. When you do that in NumPy, that is equivalent to doing this here. Temp 1 is energy squared. You made a new array for the energy squared. Temp 2 is px squared. You made a new array for the px squared. And on and so on and so on, making all these intermediate arrays. This is equivalent to that. You've made a lot of intermediate arrays. That, for instance, is why NumExpert, even though it's a virtual machine, can be faster than NumPy by not making those intermediate arrays. Numba does it too, but unlike NumExpert, it's not a virtual machine. It actually just compiles your code to native instructions. It's as if you'd written it in C, but the language you wrote is Python. So we import Numba, and it allows us to compile a function and compute a whole formula in one step with no intermediate arrays. nb.jit means jit compile, and ngit means really jit compile. I'm not going to explain the difference. Ngit is becoming the new default. It's, within a version or two from now, JIT will just mean ngit. So here's our mass formula. It's no longer an array at a time thing. It looks like the Python that we wrote above, where we create an empty array and we fill it with with this formula. So this is just defining the function, and then that is just declaring that we want to compile this. So even doing that hasn't compiled it yet because we don't know these types. So we've just created, let me, this is actually not the function anymore. This is a CPU dispatcher of the function. So it's now ready to be compiled. And when we pass in arguments, because these are typed NumPy arrays, it can use those types to walk through the whole function, assigning types to everything to compile and then run. So that step that does the same thing as if the ngit hadn't been there. But slowly. It gives you the same results. So, so the ngit doesn't change behavior. It just changes the speed. So, I didn't compute the speed on this, on doing it. Maybe you'll take my word for it. If you really want to, if you want to see it with and without ngit, go ahead and do that. Just remove it, make it a plain function, time it without, and then time it with. Since there was a question about no-gil, let me try it. See if I'm remembering the syntax correctly. No-gil is true. Doesn't look any different, but it compiles. And because I'm not doing anything in parallel, I don't remember the number before, but I don't think that's any faster. Does it compile the first time or every time? It compiles the first time only. So actually, in doing timing studies, you should be aware of that you want to evaluate it once before you do the timing study. Otherwise, the compilation will be included in the timing study. Oh yeah, I do want to show you parallel, which we don't actually need to release the GIL if we're doing the parallel internal to the function, but let's just leave it there anyway. Parallel is true. Parallel allows you to do some things like, instead of this range, numba.prange. Oh, you know what I want to do? Page top. Let's watch this go. Using all my cores, and it's actually faster. There's fast math, which uses some Intel extensions. Look up the documentation and try stuff out. I don't see any difference with fast math. I think you need to use like sines and cosines for that too. Maybe it's only doing the square root faster. Anyway, so look it up. There's lots of options, like releasing the GIL and doing things in parallel, but to do things in parallel, you have to know about prange. Does the decorator creates a CPU dispatcher? Is there a GPU dispatcher? Yes, there is. So look it up, Numba CUDA. Actually, they have both CUDA for NVIDIA and ROCm for AMD GPUs. So yes, but actually using those, you've got to know a bit more about CUDA programming. Even though you're writing Python syntax, you have to know about the semantics of GPU programming. So you have to set up like block sizes and all that. We couldn't do any CUDA examples on binders, so I didn't even talk about it here. Okay. Thank you for all these great questions. So now let's cause some problems. So what's wrong with the following? I'm going to do this. Created this new function, compute mass I, that takes in these inputs, and then given these values, these are energy 0, px 0, py 0. And now I want to do this, and I want that to run fast. I think I have the time it up above, where this one was 2 milliseconds, and this is, oh my goodness, it's 850 milliseconds. What did I do wrong? With no GIL equals true and parallel true, does Numba utilize available cores in the machine by default? I don't know if parallel works by default. I think you might need to say p range instead of range in order to tell it what to parallelize. And the no GIL, that only helps parallelization outside of Numba. So if you spawn a lot of Python threads. So, those are things to dig into. But actually right now I want to ask this question about I'm going to claim right here that this which is just typed in, although it worked, this is a terrible thing to do. Is part of the reason 850 times slower? Parallel is true? No, that's not it. So you know what? I'm going to take away all this stuff. Because really it wasn't helping a huge amount. 2.8 milliseconds versus the looping itself is what's slow. Good. Can anyone elaborate on that? That for loop is still not JITted. Yeah, I think you're there. I'm going to upvote this one. Yep. So yes, that's it. Right here, we have a for loop over this JITted function. So just having that for loop at all is one hurdle that's just getting in the way of, it doesn't matter how fast that was. We have to do this thing. But also, Numba can actually make some things slower. Entering into this function and exiting from it is slower because it has to translate Python objects into low-level objects. So really you want to design these things so that you enter and exit the JITted section as few times as possible and do a lot of your work in the JITted code. So scrolling up to the original one here, it's a key thing that I had a for loop inside. Okay. Thank you. So there's that. So what about this one? This one is as fast as the fully JITted one. So it doesn't look like there's a problem. I don't know if I would even call this one a problem, but what do you think about it? Just notice what's different about it. Just does NJIT actually do anything here? That's a perfectly reasonable question, because look what's happening in the loop is this is using a NumPy array at a time thing, which it is actually doing something. It's 7 versus 2. It does something because it recognizes this square root. And actually, I don't think we're going to be able to explain the 7 versus 2. It's going to get too much into the details. But the thing I want you to notice here, and I think that maybe you noticed it, but didn't say it explicitly, is that here we're doing NumPy style array at a time computing. Is Numba designed to speed up NumPy by default? Yes. So they might be doing something special to get 2 milliseconds instead of 7 milliseconds. They might be recognizing that, that this can be fused. Oh, you know what it probably is? Maybe they make the for loop explicitly and LLVM fuses it. Who knows? That's possible. If I call a JIT function from a JIT function, yes, I will show examples. You can call a JIT function from a JIT function without a penalty. There's a note to self to show vectorize. If you like NumPy ufuncs, such as that square root, this is a good thing to know about. Because what this has done is now this is a ufunc. This has created compute mass arrays as an array at a time function. Okay, 1 millisecond. Not really noticeable things. These are all getting into the details of what LLVM is doing to optimize things. But you just want to be out of this world and into this world. Either you have explicit for loops inside, or if you're doing array at a time calculations, you want to be aware of that and maybe try both ways, etc. So now let's talk about types, because this is the central thing in Numba. You have to be aware of types, even though Python likes to put off type checking until the last possible moment. Numba has to do type checking at compile time. So here's a perfectly valid script where the goal here is to fill an array with groups of data for each group in this set, find the maximum in each group. And before you found anything, you maybe initialize this, sorry, not the maximum in each group, the minimum in each group. You set the minimum to nothing yet. And so if you're nothing yet, you set it. And if you're smaller, if you found something smaller than it, you set it. And therefore, what goes into the output is the minimum. And here's some NumPy array with some groups. I just made it a 2-dimensional array. You can run that perfectly valid script in Python. I want to keep that there so you can see it. But now we try to run it in Numba. And first of all, this, by the way, is the same as a decorator. This is just Python syntax. A decorator just sends a function to a function. So now, invalid for Numba, suggestively named, is a CPU dispatcher ready to compile, and we give it some data, and it does not compile. It complains. And if you've used Numba before, you've almost certainly run into this somewhere. Here is a very verbose error message saying that has no implementation for built-in function LT. That's the name of the function. Found for signature LT float 64, LT literal string, which is nothing yet. So it doesn't know, so I'm translating this for you. It doesn't know less than, where the left-hand side is a number and the right-hand side is a string nothing yet, because you can't compute less than for that. The Python code, if you ever hit that point, like let me change the Python so you immediately check to see if x is less than minimum. If you were to run that, it's no longer a perfectly valid script. There is no less than supported between instances of some array and string, an array of 3 elements. That doesn't work in Python, but Python doesn't find out until it hits it. And with that guard in place, this perfectly valid script never hits it. But Numba, it doesn't matter whether you're going to hit it at runtime or not. It can't compile it because you could in principle hit it. It doesn't, it's not, that would take some serious static code analysis in order to figure out that you never actually hit it. So I think a C compiler would complain about this too. It just can't do that. And here it doesn't even matter whether there's the guard or not. You know, without the guard, and actually it would fail at runtime, still can't do it. It's just, all it sees is less than number and string somewhere in the program. Too bad. And so that's what this error message means. When you see this error message, it's kind of big and verbose, and it's like, oh my goodness, my program exploded, and it's kind of hard to read. But that's how you read these things. There's a huge amount of screen space devoted to saying, I know how to compare Boolean and Boolean. I know how to compare int 8 and int 8. I know how to compare int 16 and int 16, and so on. So it gets kind of verbose because it's telling you about all the things that it could compare. But that verbosity kind of obscures the fact that, oh yeah, less than number in a string is a problem. So I'm going to ask questions. Right now, how do we fix this up? Play around with your binder instance. And I'm going to scroll to right here. I'm sorry, I'm minimizing my scrolling as much as I can. How can we fix this program and make it work? So go ahead and try to do that. Do that in Binder. And when someone has a solution, post it in Slido. And it's okay if multiple people post. I'm going to wait until you do that. Use a very small number to hit the minimum. Okay, that's an idea. Other options? X equals group 0. Okay. And I'm going to translate this. So I'll talk about each of these in turn. And go ahead, and if you've got other solutions, put them in there. Use a very small number to initialize the minimum. Oh, by the way, the X was good. I'll get to that in a moment. If I put 0 there, kind of, but no, because these numbers are all larger than it. So if it starts with 0, it's not going to find them any smaller. So if what you really want to hear is a very large number, then it'll find minima. And if you're maximizing, you'd want a very small number. Okay. Inf, yeah, upvote that, because inf is the it's the identity of minimization. I like that idea. Although I think that's not going to work. We'll see. What do you think, Numba? Is that going to work? It works. Okay, I thought it might not work because inf means this is floating point. Oh, and the output is floating point. Okay, so that's why it might not work if you're using integers, because inf is floating point. And Numba is fine with none. That's good. Yeah, that's something where you wouldn't necessarily know that. That seems a little bit tricky. Oh, by the way, you know what? I didn't change this one, and Numba worked. Wow, there's this comparison between, it used to be a string. Sorry, no, it used to be a number equals string, and it compiled that. I'm actually a little bit surprised because this is 2 different types. It's also possible that that code path got optimized away, and then it didn't complain. I don't know. No, I'm sorry. The type checking happens before optimization, so optimization doesn't matter. So. But yes, Numba seems okay with none, and that's pretty impressive. So the type for this minimum that can be none or a number, that's an option type. In C++, I think it's not a variant, it's optional of number. This other example, by the way, of setting it to group 0, that's also good. We're redundantly checking the group 0 twice. It'd be a problem if group 0 wasn't guaranteed to exist. Like you would have a problem at runtime if these groups all had different sizes and some of them were empty. None didn't work, but inf did. This binder instance has been pinned to, now none wouldn't work if you did that without the guard, right? Let's see, is that an error? Yeah, that's an error. If you did it without the guard, but else if x is none, minimum equals x. This one here, oops, x is none. Oh, why is that not okay? Why is it not okay in Python, actually? Float in none. Minimum is none. Ah, minimum is none. You can see how this can be tricky. Yeah, if Numba, yeah, if you don't have the guard there, then the none won't work because then it'll try to do that. And this guard, Numba's typing is smart enough to realize that here you've already checked to see if minimum is none. So when you enter into here, it's not the none part of the optional anymore. Bit disturbed that minimum equals none, minimum equals nothing yet worked. Really? That doesn't work. Try it again. Try. You might, just like I did a moment ago, have be a little confused about what we're actually running. Let's see what else we got here. None for the minimum swap if minimum equals string. Yeah, okay, I guess you're describing what it did there. np.argmax group, yes. Yes, you could definitely use the built-in function. Create an extra Boolean. Oh, yeah. Use an extra Boolean instead of abusing. I wouldn't call this an abuse. I think that this is correct, but okay. That's a subjective point. But yeah, creating an extra Boolean variable, that's creating an extra flag. An option type is an extra an extra flag. If we say this here, then the runtime object is one flag for is it valid, and another slot for the value. So actually, it is that solution. It's just doing it at the level of the compiler. Instead of abusing. Okay, yeah, so I think initialize to the first value, if there is a first value. That's this. Yes, great. Thank you very much. That was great. Now I think we should move on. What is type unification? This is a word that you will see coming up in some error messages because, and Numba has gone through several revisions of their error messages. Their error messages used to be much worse, but they still have some very technical phrases in them sometimes, like type unification. So here's a valid Python script. Let's run it first and then think about what it's doing. The output is empty. You walk over these same groups as before. Oh, we're summing them now. If the total is less than 0, we return blah. I don't like that. Otherwise, we fill it and we return the output. And this is a perfectly valid script. You run it over the first 10 and you didn't have any negatives. So that's the output. You run it over everything, you'll eventually hit a negative and it returns that. So we mark it for compilation. We try to compile it and Numba says, blah, no. Can't unify return type for the following types. Literal string, we don't like negative sums, an array, and then some IR, that's LLVM assembly code, is called intermediate representation, IR. It's complaining at this line of the source code. That's good. It's giving you a line number, line 9. Output I equals total. And the other output is this return. So at least it's telling you where it is. If you look carefully enough, you can find the line numbers. So in the Slido, tell me what's wrong with this and how can we fix it? Any ideas? Raise value error instead of return. So that would be much more Pythonic. I'll do that while we're talking these. There are two types of return, string and float. Yeah, that's it. You got it. I'm going to quote you. Depending on the path returned is differ. Yes, you're right. Yes, you're right. And then I'm also going to quote you because this is what we ought to do. Yes, there's different return types, which would be totally valid in Python because it's dynamically typed, but it's not here. So anyway, this is not very nice. You shouldn't be returning strings when something goes wrong. You should be raising exceptions. And take your choice of exception. So you get the exception. You run over everything. You don't get the exception if you run over the first 10. So that is the fix. Now, why is this okay? So actually, I'm going to clear what we've got here because these are all correct answers. Why is this okay? Where, like, I get why returning a string sometimes and returning a floating point number sometimes is a problem because it can't unify the types. It can't say that these belong to a single type. But tell me, can anybody explain why raising an exception is okay? There's going to be background noises for me for about 5 minutes. So go ahead and type up. Why is that okay? Aren't we returning none? Well, no. It doesn't actually say return none anywhere. And after this will be, right after this question, look around in the table of contents for a last topic because we've got 10 minutes left after this. And we'll get to whatever you vote for the best. But don't vote yet. We're going to answer this question right now. Just be looking ahead. Not familiar with raise, but I guess the return type doesn't need to match. That's good. Actually, if you're not familiar with raise, this is a great thing to become familiar with in Python. Raising exceptions. Yeah. Other ideas? Raise would be something like throwing an error in C++. Yes, that's true. The function doesn't return. Yeah, that's it. It doesn't return, so we're only ever returning a consistent type. Like that. When raising an exception, the function does not return. Yes. Yes, that is. These are good answers. The raising is a totally different thing from returning. If we want to get into type theory, and that is a whole subject on its own, along with type unification, you can say that raising an exception returns the bottom type, the type that has no instances, the type that cannot be instantiated. But that's just a fancy way of saying that that this is not returning a value. It's like this function didn't return. It's this, computer scientists would say that raising an exception is kind of the same thing as the function running forever, like in an infinite loop. it's not returning. Other things, okay. Okay.
Jim,
so that
sorry,
I know that there's
the thing is on again.
I know. That's my daughter swinging, and that's why I said I'm going to have background noise for a few minutes. Okay. So, right now we have 10 minutes left, and I'm going to ask for people to again use Slido and vote for the last topic. I can stay for about half an hour after. Awkward array, okay. So both answer and vote, because I'll pick whatever comes up on the top of the heap. The other things that I have prepared are some suggestions to avoid lists and dicts. They are very common in Python, but they don't work so well in Numba because things have to be typed. Closures versus arguments. If you go fancy with your functions, there's certain things you don't want to do. You want to just use plain functions. Functions calling functions. There was a question about this already. That's perfectly fine. Functions calling, like a JITted function calling a JITted function runs at full speed. It even inlines them if it can with the optimizer. Functional functions, actually, Numba supports a little bit of functions passing functions. It's kind of crazy that they went that far. Classes, I would kind of argue against JIT class. I've not had good experiences with it. I managed to get an example working in the notebook, and that was actually after a lot of trial and error. So I don't think that the JIT class, which is an experimental feature anyway, is all right, useful for day-to-day programming. Auto-generating functions, this is a great thing to do when you have a JIT compiler. So that's something we could talk about. How to debug. You know, you can use GDB, but I don't. I write print statements, and print statements work in these functions. Awkward arrays with Numba, with awkward arrays as arguments or as return values. So let's see. Awkward arrays with Numba and auto-generating functions. That's a clear distribution. I'm going to just jump to awkward arrays. And if there's any time at the end of that, I will go and do auto-generated functions. Okay. And avoiding lists and dicts. If, you know, in the overtime, I'll see if there's time for that. So awkward arrays can be arguments. So here's how you might end up getting some awkward arrays. If you open a root file with uproots and ask for some arrays, by default, you get awkward arrays. And you can tell because array is capitalized. NumPy lowercase their arrays. So if you do library equals NP, you get a NumPy array, which is actually pretty complicated in this case because it's multiple fields. But if there's an awkward array. One of the advantages of an awkward array is that you can pass them into Numba compiled functions and walk over them as structured data. NumPy arrays are just numbers, you know, maybe multiple dimensions, but they're just numbers. Awkward arrays are variable length lists. There are records like this one. These are Lorentz vectors. Let me give a little bit more detail on this. Muons 0 to list. So we can see in Python it would look like structures like that. So these structures that contain FP, you know, and FX, FY, Z, and FE. So so that's logically what this data is. But you can pass it into Numba because there's a lowered version of these data structures. So here, what I'm going to do is going to get the ZMass with the wonderful Python particle library. So you don't type in ZMass by hand anymore. I'm going to use a function called by a function. So this is a helper function to compute a single mass given to 4 vectors. And we are using like dots. These are the C++ member data, FP and FX. That's inside of a Lorentz vector. That's where that came from. So coming straight from root. And then we're looping over these variable length groups of particles. They're grouped by events, finding a best candidate, and the best candidate is the one that whose mass is closest to the Z mass, and we're doing something a lot like before, and we're using this none because we can do that. By the way, I'm just going to try to remember for myself auto-generating functions and lists and dicts are next before I clear this. Auto-generating functions, lists and dicts are next. Okay. So we define this function, and it walks over this stuff as if they were just those Python objects, and we can do that. We run over the muons. Let's instead run over the jets. No problem. Incidentally, if you're doing the same thing with array at a time functions and awkward array, actually, this thing of finding the thing that's closer to the Z mass is quite a bit more complicated. If you're doing array at a time calculations, you have to make combinations, use a vectorized function for the mass, define a metric for closeness to Z, argument that, select them, and that's, you can do it in an array at a time way, but this is probably easier to think through. And that actually was one of the criticisms of awkward zero, and why it was rewritten to be able to do this, so you can use Numba. So big advantage of awkward array versus structured NumPy arrays in Numba. You can check on this one. I don't think the structured NumPy arrays work in Numba. You can check. They might have fixed that by now. But also structured NumPy arrays are still flat objects. You can't have variable length lists of them. They're basically just what in awkward array would be called a record array. So the advantage is that you can do more data structures. Okay. So what you do, whether you do it array at a time or element at a time, is whatever's natural for you. When you're doing an analysis, you're working on a command line or Jupyter Notebook or something, interactively working these things out. And you can interactively do array at a time calculations immediately and see the results of them immediately. Whereas if you are writing for loops, you have to, write the whole for loops. So there's trade-offs, and so you have both methods, and you can jump back and forth between them. Generally speaking, element at a time calculations will be faster than array at a time calculations, just like for NumPy, as I showed in the very beginning of this. They'll use less memory because we're not, creating a bunch of combinations and then walking over them in a flat way. It'll require more lines of code to write for loops, and it will require more fiddling to get the types right. If you're doing array at a time calculations, it'll require fiddling to get the indexes right. If you're writing Numba functions, it'll take some fiddling to get the types right. So, nothing's a silver bullet, but you work it together, you cobble it together with what you've got. It's also a good technique to use Numba to make arrays of Booleans or arrays of integers that you then use to slice awkward array. So you can go back and forth a lot. Like this function here makes a mask. It's returning an array of Booleans. And then you can take that array of Booleans and use it as a mask. So the point here is not use one instead of the other, it's to use them together. Awkward arrays can be return values. And here the story gets a bit more complicated, as I have 1 minute left in this tutorial. The one thing that you can do right away is you can return part of your input. Like you can loop over the groups of particles, and when you find a nice one, return that. And that can be especially good if you're debugging. You want to find that one event that's messing everything up. So you write a little function to quickly get to that event, and then return it so you can, you can analyze it offline. And then if you're just talking about one event, you can convert it into a list and look at it. I mean, Python objects, turn into Python objects and look at it. But if you want to make an awkward array, that's trickier. And make a whole new structure that didn't exist before. We need a syntax for constructing it. And that's what array builder is. There is awkward array, Python reference. There's a lot of documentation on array builder here. But array builder works in Numba. So this, so this array builder that I'm using outside of Numba to build a little awkward array of 1, 2.2, and 3. You can, or make a record with X, Y, and Z fields. And then you can turn it into a real awkward array with snapshot. You can do that in Numba also. So how are array builders and arrays different? Arrays are immutable objects. They can be transformed to new arrays, but they can't be changed in place. Array builders are append only. You can put stuff at the end. Yeah, and they start specific and get more general. I'm going to skip that. The point is that you can use array builders in Numba. So if you needed to make variable length lists of Booleans, like this guy here, take a snapshot of it. There's an array of some 2,000 variable length lists of Booleans. This first one has 2 in it. This last one has 1, so that you can use it as a jagged slice on an awkward array. You can do that by building it with array builder. Some limitations, Numba doesn't support the with segment yet, so I'm looking forward to that. Because then we can use with builder. But then if you don't have it, you just say builder begin list, builder end list, builder begin record, builder end record. You can't create an array builder inside the function. You have to pass it in. You can't snapshot it inside the builder. You can do that outside. So this is, again, working with the whole idea that a Numba JITted function is a brief excursion into compilation land. So you do most of your complicated analysis stuff in Python because it's easy. Then there's that one thing you want to accelerate. You make this JITted Numba function do just that one little thing with as plain and simple and numeric code as you can, including array builder. But you don't make the array builder inside, you pass it in, and you don't snapshot it inside, you snapshot it outside. So yeah, so that's how you use it. You got to have this philosophy in mind of Numba is for brief excursions into low-level compiled stuff. And that actually is why it's got these factors of hundreds of thousands faster than Python, whereas PyPy can only be factors of several faster than Python. It's because in attempting to compile the whole language, in taking that philosophy that we want just everything to be compiled, it doesn't isolate the things where the hurdles need to be removed. And Numba forces you to think about removing those hurdles, which is, it's too bad that it forced you to think about these things. It'd be better if it just worked automatically. But it guides you toward the most optimized code you can have. So that is, I'm out of time for the normal part of the session. If you've got other meetings, I'm sorry, I'm actually 4 minutes over. If you've got other meetings, be aware that you've got to get out and go to those other meetings if you have them now. Otherwise, I have another half an hour before my next meeting, and I can keep talking about things. Like there was a request to talk about lists. Okay, how about Numba and SciPy? Great question, because, you're welcome. The Numba and SciPy, there is a project. Originally it was going to be called Scumba, which would be great, but they backed off from that. There's a project to Numba optimize SciPy. But more importantly than that, Gitter, somewhere in one of these Gitters, not uproots, but is it here? Hans told us that he has written a Numba stats. So check this out. Numba stats does a lot of the statistical functions from SciPy, but in parallel, the Numba team is actually working on SciPy. Okay, great. Now in my remaining time, I'll talk about lists and dicts because I remember that was a request. And then third after that was auto-generating functions. And I'm still open to questions. And since we'll probably have fewer people in this part, well, there's still 61 participants, so yeah. You can interrupt by voice, but this chat thing is I found it to be better. All right, lists. Why avoid lists and dicts? It is actually possible to use lists and dictionaries. The problem is that Python before recently, when you make lists and dicts, they were always untyped, and so the language didn't have much support for type annotations. As you all know, Python has great support for type annotations now, and Numba is running to catch up. But that means that when you write a normal Python function, let's see, does this one work? Yeah, this one works. You don't say anywhere what the type of the elements of that list are. Numba can sometimes figure it out. Like here, because the only time we're appending, we're putting numbers into that list, floating point numbers, then it retroactively knows that that is a list of numbers. If you tried to append two different types of things into it, I suppose you would have some problems. I suppose it would complain. Imagine it would complain. Yeah. It's doesn't say type unification, but it's got some problems. Resolving typing. Here's the two problems: append total versus append hello. Because it wasn't able to type it. Now, oops. That said, this typing doesn't always work. I thought I had some examples here of places where it failed. Okay, it was just assuming that I would remember how to make it fail. How can I make that fail? I thought I had all sorts of examples where I was passing in. No.
Jim, what would happen with the list of lists, but each sublist had varying length?
In principle, so it's type system, which I had nb.typing.list. No? Yeah, its type system allows you to make lists of lists. And I have had trouble with that before. I've tried making lists of lists or make dictionary whose values are lists. And you get a little bit beyond the simple stuff and you run into things that don't work. And I think I had a mental note to myself that I was going to modify this function and make it not work, but I'm hard to think on my feet. To make it fail, initialize with a string, puppet, and then add numbers. Oh yeah, that makes sense. Yeah, that's good. So elho, pop, sure, that'll fail. Because actually in the Numba documentation, okay, I'll get to that C++ question in a moment. In the Numba documentation, they even say sometimes you want to do this. You want to do something like I don't remember the exact example that they had, but they even suggest stuff like that, where you say, okay, take nothing out of a NumPy array of integers and pass it into that output. No, that wasn't it. Something like that. But they make suggestions like that in the Numba documentation to trick it into knowing the type. Now, is it possible to explicitly specify types as in C++? Yes. You can, right up here, you make a list of the signatures that you want to have. Now you say like C++, yes, but you have to use Numba's type system. So the question is, will I get it right if I just try to do this? Maybe it's parenthesis. So signature, Numba, to make an array type, it's float 64, and you do that to make an array type. So that, I think that is the correct signature for this. It is not. It's not the correct signature, and that's how you can spend a lot of time trying to express the types correctly in Numba's type system. You can spend a lot of time doing that. A better way to do it, actually, is to make this a correct function, right? Okay, so correctly compiled. And because we ran it once, it has been compiled. And look at the keys of its overloads dictionary. And it says that, oops. Now this is Python being cantankerous about a SB list to take the first one. It says that that's the type. That doesn't look like a signature to me. That's the array input. Oh, the overloads is the list of argument overloads. So this is a type. And can I even just put that NB, make an array type? But you can do that with float 64. And that is the only argument in this. So it has to be a tuple. Nope, that wasn't it. By the way, you get typing errors right away because if you put specific types into this list here, it compiles it immediately instead of compiling it the first time you call it. But there's no way I could, off the cuff, get the type annotations right because they are, they're kind of hard. So that's why it'll be great when Numba adopts Python's type annotations, because then, we know how to write Python type annotations. It'd be great if they just pick that up. Now, those will always be Python annotations. They're not going to be C++ syntax. It'll be some other syntax, either Numba's or eventually, hopefully, Python's. Is it possible to pre-allocate memory in a Numba list and help performance? In a list, I don't think so. You pre-allocate arrays, and that's a, and I think you'll always get better performance if you're using arrays rather than lists. The reason that we like lists is because you can append them. So you can start filling it before you know how many things are going to be in it. That also is an argument for Array Builder. I'm going to be kicking myself afterward because then I'll remember what it is I wanted, how I wanted to modify that and show that every working Numba program involving lists and dicts is just a few little steps away from a non-working one. So I think it's better and same thing for the JIT class. It's cool. Let's see, classes. What about classes? It's cool they have a JIT class, but it's rather hard to make it work. Oh, typed. See, not types, not typing, but typed. Yeah, that's where you spend your time if you're trying to specify type annotations. It's much better to just run it on the data and it'll pick up the types that you need. All right, now the third thing that you wanted to hear about was auto-generating functions. Yeah, this is a good thing. If we're living in a world where stuff is compiled little by little, just as soon as you need it. You can use your favorite programming language to produce the code for those functions. And this is a very powerful technique. This is why Lisp users said that Lisp is better than all other languages all through, the first 50 years of its existence until it became a thing that we can all do now. This idea that metaprogramming, that you can use the programming language you're in to write programs in that same programming language. We can do that here. So just like in Python, where you can make a function like this one, print code. This is a string, and it's been created for exactly 5 arguments. And included in that string is the numba.vectorize. Now, when we execute that code and have now created and compiled created the function, we give it some arguments. It has been compiled for exactly 5 arguments. So the 6th one in there, and it's not compiled for that. Oh no, why did it work? Oh, because I changed the code. Look at that. Because I forgot the fact that I have this thing here. This is a powerful technique. Great power, great responsibility. You can make some really convoluted code if you use this too intricately. Like maybe I shouldn't have made this an F string where that stuff is inlined with the stuff. Maybe I should have broken it out into a few more lines and printed out in between bits so that I can show, so I can debug it more easily. But this is a great technique to be aware of. Also, Numba has built this in. If you want to have a function that does different things based on its types, if you're doing this in C++, you get into type metaprogramming. You create templates and you overload individual templates with the syntax that looks like that, and then you define your function and all that kind of thing. In Numba, the way to do that is use Numba generated JIT, and then this outer function here is a function on types. Data and mask are 2 Numba types. So you can check, is this type of mask none type, or is it not? And you return a function that you want it to compile for each of those different types. And this is better than trying to fiddle with getting the type annotations correctly the way that I was before, where I had to get the type annotation exactly right. Here, you're just asking a general question about the type, and you're asking it in Python so you can use the full power of the Python language to ask, very specific questions about this. Is it a 2-dimensional array or a 1-dimensional array or whatever? Yeah, I'll clean up the board. Sure. And then, like, if you've got data and mask and they're both arrays, let me scroll. When you, did I not? Because I didn't run it. Okay. It uses the second version of this function because data and mask are both arrays. And here it uses the first version of the function because the second thing is none. And you can dream up examples of things to do with that. But here I've just optimized this so you don't have to mask over empty masks. So this is more constrained than the full, make a string with whatever code you want in it. Okay. Right, okay, I'm getting little reminders that in 10 minutes I've got to go, but I still got 10 minutes. At this point, there's still a lot of people here. Huh? Thanks. I guess I'll talk about debugging, because actually when I was imagining this tutorial, this is kind of what I had foremost in mind, that yeah, it's great to have a rundown of the lists of all the features that Numba has, but the real thing is, what are some best practices for developing this? Like, I'm giving kind of simple examples, and you might say, okay, but my analysis code is this big complicated thing. This is not representative of what I'm trying to do here. Well, I would argue that this is the best way to use Numba, even if you have something that you need to do that is complex, because I take a two screens approach to this, or a two windows approach, where on one side, you've got the code that works, written, say, in pure Python, or written with array at a time functions, and you want to speed it up. And on the other side, you've got the code that you're writing. So you're basically rewriting it, but with guidance from the working version. And you rewrite it in little bits. You make little functions that do one thing and get that to type, and you're doing it interactively. You're not writing a script and then running it and hoping everything works. You're doing it little by little, getting feedback as you go along, so that if one of your tiny little functions doesn't type correctly, if it fails a type check, you find out about that immediately and fix it, because if it's a small function, it's an easy problem to fix. So if your workflow is edit the script, save, run from the beginning, edit the script again, especially if run from the beginning means load a very slow big data set, then you might as well be using a non-JIT compiler like C++. The way that you benefit from this is by interacting. So here are the recommendations. If you're still figuring out what the logic is, use pure Python functions and work on small data sets. If you have an algorithm and you want to make it fast, well, you could just start by just throwing njit at the top of it and hope for the best. Maybe you'll be lucky. Try it. No harm in trying. If that doesn't work, break it down in small pieces and njit each piece individually. And then also print statements work. And that has been enormously useful. Either they didn't work early on, or I just guessed that they wouldn't work, because print is the kind of thing you don't expect to work in this very low level environment. In fact, it works, and that's great. And so we should use it. And you know what? I'm slapping my forehead now, realizing I never tried print on an awkward array inside of a JITted function. And if that doesn't work, I should make that work, because print is great. So those are my recommendations on debugging. Other questions? This has been open the whole time. If we've got minutes left before I have to leave here and go to my next meeting. Any last minute questions? I'll put the table of contents up again. And actually, I talked about everything. Look at that. I've talked about everything except for functions calling functions and closures and stuff, but that's okay. If there's no actual questions, then we're 25 minutes over time. Wow, awkward array print works? Cool. All right. Either I did that once and just forgot, or something I did made it automatically work, which is convenient. All right, cool. Thanks, guys. This has been great. Oh, yeah, and then if you're ever looking for this again, I will put a recording of the session up on this GitHub. It will also go, and that's going to point here. That's where all of this will be. And as a reminder, this is the first of many. Jackson PyHEP next time. And I'll see you all next month. Right.
Thank you very much, Jim.